All right, welcome back to 2241. Here is the explanation video for the formulas for section 1.1. We're going to go over the distance formula and the equation of a sphere. Note also that this is not a required video. It is simply there to help you understand the formulas a little better. Okay, so what we had for the distance formula was a couple of points, P1 and P2. You can see those right here, and I've drawn them here and here. And we want the length of a line segment between the two of them. We want a formula for that. So we actually know what that is already. It was in the formulas. But here we're going to derive it. So what do we do? Well, I've also drawn some lines here and marked a few right angles. Then there's also this one line down here. So let's start with the line that we actually want. We want this line D. And actually, I should mark another one, but I think I'll just point it out. There's a right angle right here between this line B and the line delta Z. So if I pull that triangle out and put it over here, I can draw it like this. And what we have is that this is our delta Z, that's D, and this right here is the thing that I labeled B in the diagram. And so we want to know, right, what is D? Well, I can write down a formula for D, since that's now a right triangle. D squared, then white, D squared equals B squared plus delta Z squared. Okay, cool. So delta Z is given. Remember that delta Z or delta X or delta Y is just the difference of the two coordinates. And in this case, it doesn't matter whether you have 1 or 2 in front because we're going to square the difference. Okay. So now what do we need? We need B squared. What is this thing? Well, we have another triangle in our diagram over here, which we can also pull out. And we'll draw that right here. To move that a little bit. Longer, move it there. Okay. And then we have another line. And so now the hypotenuse of this triangle is B. You can see that over here in the diagram. And the lengths of the legs are delta Y and delta X. Okay, so we have another formula, or another Pythagorean theorem formula that we can write down. B squared equals, well, delta X squared plus delta Y squared. Oh, and then what do we do? What do we get if we put these two things together? Well, I take B squared and plug it in there. Let's move this up and give ourselves a little more space. I'm gonna do that. And so what does this look like? We get that D squared equals delta X squared plus delta Y squared plus delta Z squared. And now if I solve this for D, I just take the square root, and I'm going to take the principal square root, means the positive one, and I'll have exactly the formula that we wrote down in the other video. Okay, and so there is the distance formula for the length of a line segment between 2 points, P1 and P2. Okay, so now we're going to talk about the equation for a sphere in R3. Remember, R3 is just XYZ space. That's a short way of saying it and writing it. Okay, so I have a statement here that I've written down, and we'll just read through it. So it says S as a subset of R3, so that's what this symbol here means, subset, is a sphere if there is a point C equal to ABC in, this symbol means inside of, R3, and a number R greater or equal 0, so that for every point P, the distance from P to C is equal to R. And I have a picture of that right here. So again, we have our three-dimensional coordinate system and a sphere drawn in here. And if I pick a point P on the surface of the sphere and draw a line segment to that point C, then no matter where I pick that P, could be over here, maybe over here, somewhere in the back, and draw a line to C, that line will have the same length, no matter what. And the claim is that if there is such a point. Okay, so, well, if I look back at this formula right here, well, the distance is fixed for a sphere. So I'm just saying that the distance is fixed. So let's draw or write that out. The distance from P to C is going to be equal to, actually, square root of, well, I want x minus a, I suppose I should say P equal x, y, z squared plus y minus b squared plus z minus c squared. And this is me just plugging in for those delta x, y, and z's. Okay, well, I also know that this is equal to r, and so I have r squared equals x minus a squared plus y minus b squared plus z minus c squared. And wouldn't you know it, that's the formula for a sphere S. So what I'm saying with this equation is that all of the points P equal x, y, z, which satisfy this equation, form this sphere in blue over there. And it comes directly from the distance formula for the distance between 2 points. We just fix that point C and then allow P to vary as long as R is constant. All right, and that is the explanation for the formulas in section 1.1.